Alright, hello everybody. This video is going over the textbook questions found in Reactivity 1.3. This is the practice questions section at the end of this section of the textbook, and it is numbers 1 through 10. So we will be going through all of those today. Number 1 says, it is now widely accepted that the increased production of carbon dioxide is leading to global warming. A says, describe how carbon dioxide acts as a greenhouse gas. So I put this visual here for you on the bottom right so you can kind of follow along as I explain this. So the first thing that happens is the sun emits energy in the form of visible light, which is going to pass through Earth's atmosphere and warm the surface of the Earth. The Earth's surface is then going to radiate heat in the form of infrared radiation back towards space. Now, once that happens, the CO2 molecules, they can absorb that infrared radiation and then re-emit it in all directions, including back towards the Earth. When CO2 re-emits that infrared radiation, it slows down the escape of heat from Earth's surface into space, and that's going to keep the planet warmer than it would be without CO2. Now you can see A was worth 2 marks, so they are looking for 2 specific things. The first mark was that you have infrared radiation from the Earth's surface, and some of the radiation is absorbed by gas. I do want to note that IB specifically said in the mark scheme that it would not accept the word trapped or blocked, and it would also not accept that the infrared radiation was from the sun, because again, it radiates from the sun into the Earth's surface, and then the infrared is coming from the Earth's surface, not from the sun. The second point from the mark scheme is that radiation caused increased vibrations in bonds and re-radiates heat back to the Earth. And the IB mark scheme specifically said do not accept the word reflects or bounces. Then B says, outline why oxygen and nitrogen, which are more abundant in the air, are not greenhouse gases. So to understand this, we need to look at the actual structure between greenhouse gases and oxygen and nitrogen gas. So for a molecule to absorb infrared radiation and act as a greenhouse gas, it has to undergo vibrational changes that create a fluctuating dipole moment, which is an uneven charge distribution. So with greenhouse gases, they are going to absorb and re-emit that infrared radiation due to their ability to vibrate in response to infrared radiation or infrared wavelengths. So because oxygen gas and nitrogen gas are diatomic molecules, they have symmetrical charge distribution, which means that they cannot absorb that infrared radiation. This means that the IB was looking for something along the lines of that there was no change in the dipole moment when the molecule vibrated due to infrared radiation. Continuing on with number 1, C says identify 2 pollutants other than carbon dioxide that are produced in the combustion engines of cars and outline their polluting effect. So besides CO2, I know we're going to have carbon monoxide. Carbon monoxide is going to be formed when the fuel burns incompletely due to a lack of oxygen during that combustion process. So when we're talking about carbon monoxide, the polluting effect is definitely going to be that CO2 is going to bind to hemoglobin in the red blood cells. And when that happens, it's going to reduce your oxygen transport and lead to dizziness, headaches, and in extreme cases, death. The next pollutant we're going to talk about is soot. Soot, or particulate matter, which is PM in the diagram to the right there, consists of tiny carbon-based particles produced by the incomplete combustion of fuel. Diesel engines in particular create large amounts of that black carbon, which is a component of soot. And then you can have really fine particles of soot that can penetrate deep into the lungs, which can cause asthma, lung cancer, and different cardiovascular diseases. And then finally, we have our nitrogen oxides. Nitrogen oxides, or NO gases, are going to form when high temperatures in car engines cause the nitrogen gas and the oxygen gas in the air to react. When these nitrogen oxides are produced, they can react with volatile organic compounds in sunlight to create ozone, which is a very strong component of smog. Another polluting effect of nitrogen oxides is when they react with water vapor in the atmosphere to form nitric acid, which falls as acid rain, which can lead to a ton of environmental issues. So to get the 2 marks from C, you had to have 2 of these 3 options. Number 2 starts with A. Most of the world's energy comes from fossil fuels. State 2 reasons for this. So fossil fuels like coal, oil, and natural gas remain the dominant energy source worldwide at this point in time. There's a lot of reasons for that. The first one is that they produce energy at an appropriate and efficient rate. Fossil fuels contain a high amount of energy per unit of weight compared to alternatives like solar and wind. For example, gasoline provides about 46 megajoules per kilogram, while lithium-ion batteries in electric cars provide around 0.25 megajoules per kilogram, which is almost 200 times less. The next point is that it's easy to transport. So because of the high energy density, a small volume can contain a large amount of energy. This makes them convenient to store and move through pipelines, tankers, or trains across long distances, while the established infrastructure is already in place. Another reason would be that fossil fuels are widely available in many regions, with large reserves in countries like US, Saudi Arabia, Russia, and China. So while extraction costs do vary, coal and natural gas remain some of the cheapest energy sources currently available. And then another reason would be that our current tech is based on fossil fuels. The world has over a century of investment in fossil fuel infrastructure, including power plants for coal and gas fired, or pipelines and refineries for oil and gas stations for transportation. Replacing that system with renewable energy would require massive investments in new technologies like battery storage, smart grids, and EV charging stations. So to get full marks for A, you would need 2 of those 4 options. Then B says the specific energy is the energy produced per unit mass. Identify a fuel which has a higher specific heat energy than fossil fuels. So to get the answer for B, all you would have to do is write hydrogen. I know we've talked a lot about hydrogen and how it has a very high energy content. On the diagram to the right there, you can see just how more energy producing hydrogen is compared to the fossil fuels we were just talking about. Now we know because we've already talked about this, but remember, fossil fuels consist of carbon and hydrogen, and when those fossil fuels are burned, the carbon atoms from the fuels produce carbon dioxide, which requires energy to produce, reducing the total available energy output. With hydrogen, it does not have carbon, and it avoids that energy loss, making it much more efficient per unit mass. All right, moving on to number 3, part A says determine the percentage of carbon by mass in the fuels coal, petrol, and natural gas. So remember, in order to get your percentage of an element within a compound, you're just going to put the mass of that element you're trying to find over the mass of the entire compound. So for coal, the formula is CH, so we take our mass of carbon over the mass of C plus H, which is 13.02. Multiply that by 100 and we get 92.2% carbon. It is the same concept with petrol, with a total of 8 carbons at 96.08, and then the entire compound at 114.26. Divide those and multiply by 100, you get 84.1% carbon. And then when you do the same process for natural gas, you get 74.8% carbon. Moving on to part B, it says, suggest 2 reasons why coal has been replaced by petrol and natural gas in many countries. So I hope after doing the math for part A, you can see that coal has a much higher percentage of carbon than natural gas and petrol. So I hope that kind of leads you to at least one of your answers for part B. Another reason you could put for why coal would be replaced by petrol and natural gas is using that energy content we talked about in the previous slide. If you look at it, the energy output for coal, which is number 2, is much less than it is for petrol and natural gas. Another reason they would have taken for B would be that it is easier to transport. This is because petrol can be stored in tanks and pumped easily, making it ideal for automobiles, airplanes, and machinery. And natural gas can be piped directly to homes and industries, eliminating the need for manual handling with coal. And coal is also really bulky and heavy. And then part C says one fuel that has been proposed as a replacement for carbon-containing substances is hydrogen. State 2 advantages of using hydrogen as a fuel. 2 of the answer choices that we've already kind of discussed is that hydrogen has a very high specific heat energy, and also that it's very clean burning because the only thing that it's going to produce is water. Another proposed advantage that you could talk about for C would be that it can be generated by electrolysis, which would technically be a renewable resource. Number 4 says the enthalpies of combustion of propane and butane are given in section 14 of the data booklet. Part A says calculate the heat produced by the combustion of 1 gram of C3H8 and C4H10 in kilojoules per gram. So we are trying to solve for kilojoules per gram. We know that our molar mass of C3H8 and C4H10 can be derived from the periodic table. So for C3H8, that's going to be 44.11 grams per mole. And then for C4H10, that's going to be 58.14 grams per mole. From section 14 of the data booklet, we can get kilojoules per mole, or the enthalpies of combustion. So for C3H8, we have negative 2,219 kilojoules per mole. And then for C4H10, we have negative 2,878 kilojoules per mole. Now remember, what we're solving for is kilojoules per gram, and we have grams per mole and kilojoules per mole. So technically, if we take our kilojoules per mole and divide our grams per mole, our moles will cancel out, and we're left with kilojoules per gram. So for C3H8, we're going to take our enthalpy of combustion, which is 2,219 kilojoules per mole, and divide it by our molar mass, which is 44.11 grams per mole. Our moles are going to cancel out. We're going to be left with kilojoules per gram, and that will give us 50.31 kilojoules per gram. And then we're going to do the same thing for C4H10. So we have 2,878 kilojoules per mole, and we have our molar mass of 58.14 grams per mole. That's going to give us 49.50 kilojoules per gram. So that would be our answer for part A. All right, B says use the ideal gas equation to calculate the density of the 2 gases at STP and hence calculate the heat produced when 1 centimeters cubed of the two gases are burnt. So the first step is getting the density of each of our two gases. To do that, we need to make sure we understand the ideal gas law and the density equation. So density is also written as a lowercase p, and density is mass over volume. Now, looking at our ideal gas law, we know that we have moles, which is the lowercase n, and we know if we are solving for moles, that's going to be our mass over our molar mass. That's how we get moles, right? So if we were to sub that in for moles, we would get PV equals lowercase m over uppercase M times R and T. Now, if we brought volume to the other side, we'd end up getting pressure equals lowercase m RT over molar mass times V. Now you can see here we have mass over volume in this equation, which is density. So now if we sub in density for those two units, we end up getting P equals density RT over molar mass. So now if we wanted to isolate that density, that lowercase p, we'd end up getting pressure times molar mass over R times temperature. So that would give us our equation that we're going to be using for density of the two gases. So now let's put that to use with propane. So with propane, we're solving for the density. We know we're going to be using our gas law of 0.0821 liters times atmospheres divided by moles times Kelvin. So because I'm using that specific gas law, I need to use 1 atmosphere as my pressure because that is standard pressure. And then I'm going to have my molar mass of propane, which is found to be 44.11 from our last problem, and that is grams per mole. Then we're going to be dividing it by our gas constant, which I already told you we're going to be using 0.0821 liters times atmospheres over moles times Kelvin. And then we have our standard temperature at 273 Kelvin. So now we're going to go ahead and solve for the density. That will give you 1.97 grams per liter, which is density. Now we're going to do the same thing with butane, or C4H10. Using our equation we got, we're going to again use 1 atm. Use the molar mass from our last problem, which was 58.14 gram per mole. We're using the same constant. And the same temperature because it's standard temperature and pressure. When we do that, we end up getting 2.59 grams per liter, which is our density for butane. So now that we have density, we need to calculate the heat produced when 1 centimeter cubed of the two gases are burnt. Now to get our final answer for this question, which is the heat produced, that means we're solving for Q. And to solve for Q, we're going to be multiplying our moles times our enthalpy of combustion. So in order to get our moles of propane and our moles of butane, we need to take our density and multiply it by the volume given, which in this case is 1 centimeters cubed. Now, since our density is in grams per liter, we need to go ahead and convert 1 centimeters cubed to liters, which would be 0.001 liters. And now that we have mass of propane and mass of butane, we can go ahead and divide them by the molar mass in order to get moles of each. So remember, for our propane, we had 44.11 grams per mole. And for butane, we had 58.14 grams per mole. And now that we have our moles of propane and moles of butane, we can go ahead and multiply them by the delta H of combustion in order to get our Q, or our heat produced. So that would give us 0.099 kilojoules per gram for propane and 0.128 kilojoules per gram for butane. All right, next is number 5. A says, state the name of the process by which green plants capture the sun's energy and convert carbon dioxide and water to glucose. I really hope this answer was the easiest one on the textbook work, and the answer to that would be photosynthesis. B says, state the overall equation for the full redox reaction of photosynthesis. That would be 6CO2 plus 6H2O reacts to form C6H12O6 and 6O2, and it did not require you to put states of matter for that reaction. And then C says glucose can be converted into ethanol, which can be used in fuel cells. Identify this process by name and write the equation for the chemical reaction. This is called fermentation, as done in our notes. And fermentation's chemical reaction would be C6H12O6, and it decomposes into 2C2H5OH, which is ethanol, and 2 moles of carbon dioxide. Okay, number 6 says, use section 14 of the data booklet to calculate the specific energy of methane and methanol. So in order to calculate specific energy, all we're going to do is take the enthalpy and divide it by the molar mass for each of the compounds. So in this case, we have methane, which is CH4. If we look in our data booklet, our enthalpy value is going to be 890 kilojoules per mole, and our molar mass is 16.04 grams per mole. So when we solve for the specific energy of methane, we will get 55.5 kilojoules per gram. And then doing the same thing for methanol, from our data booklet, we get an enthalpy of combustion of 726 kilojoules per mole, and our molar mass of ethanol is 32.04 grams per mole. So when we solve for that, we get 22.7 kilojoules per gram, and that is the other mark for 6A. Now, as you can see, methane has a much higher specific energy than methanol does, meaning that it's going to release more energy per gram when it's burned. And this makes methane a much more efficient fuel to use, though methanol is a little bit easier to handle because it's in liquid form. B says, deduce the average oxidation number of carbon in the two compounds. So first, let's start with methane, which is CH4. So in CH4, we know carbon is more electronegative than hydrogen, which means hydrogen is going to assume a +1 oxidation number. So if we have C as our X value, that means we have X plus 4 times a +1 charge equals a total charge of the compound 0. So if we do that, that means we have X plus 4 equals 0, which means our oxidation state for carbon is -4 for methane. And then if we do the same thing for ethanol, we have carbon, which is what we're trying to find out. We have 4 total hydrogens. Again, since the other ones are more electronegative, those are going to assume a +1 oxidation state. And then we have oxygen, which assumes a -2 oxidation state. So that's going to be equal to 0 because there's no charge on the overall molecule. So when we solve for that, we get X plus 4 minus 2 equals 0, which means if we solve for carbon, that's going to give us a -2 oxidation state. So carbon in methane has a -4 oxidation number, and carbon in methanol has a -2 oxidation number. C says, suggest a possible relationship between the oxidation number and specific energy. So as you can see, our specific energy of methanol was higher and the oxidation number in methanol for carbon was higher. So there is a direct relationship between the oxidation number of carbon and the specific energy of a fuel. And the key idea is that the more reduced or negative the carbon, the higher the energy released during combustion. Please note that you would also get points for going the other direction. If you said the more oxidized the carbon, the lower specific energy, that would also give you the mark for C. D says calculate the specific energy of glucose and discuss the validity of your hypothesis in part C. So we know glucose is C6H12O6. We know that hydrogen is going to assume a +1 charge. Oxygen is going to have a -2 charge. So when you add those up, they're actually going to cancel each other out, which means that our carbons have an oxidation number of 0 in glucose. So since our oxidation state for carbon is 0, now we want to figure out what the specific energy of glucose is so we can compare it to our relationship in part C. Now, using our booklet, we're going to do the exact same thing we did in part A to get the specific energy of glucose. So we get our enthalpy value, which in the book is 2,800. That's going to be kilojoules per mole. And then using our periodic table, we can get the molar mass of glucose, which is 180.16 grams per mole. So that's going to give us a specific energy of 15.5 kilojoules per gram. Now, if we're looking at our oxidation numbers in methane, which is -4, our oxidation number in methanol, which is -2, and then our oxidation number in glucose, which is 0, that is going to follow the same trend. As those numbers increase and become less negative, they are going to have a lower specific energy. So it is going to be a valid hypothesis from part C. Seven says fuel cells may be twice as efficient as the internal combustion engine. Although fuel cells are not yet in widespread use, NASA has used a basic hydrogen-oxygen fuel cell as the energy source for space vehicles. Deduce the half equations occurring at each electrode in the hydrogen-oxygen fuel cell in an alkaline medium. Before we deduce our half equations, let's make sure we understand the overall idea of this fuel cell. Now, in this fuel cell, we are combusting hydrogen, right? It's a combustion equation where we have hydrogen gas as our fuel, we have oxygen gas as our oxidant, and we are forming water. And then we're going to go ahead and balance that. And before we are able to actually identify what's happening at the cathode and what's happening at the anode, we need to know the oxidation numbers of hydrogen and oxygen in our equation. So if we look at our reactants, we know as elements, they're going to have an oxidation number of 0. And then in water, hydrogen is going to have a +1 oxidation number, and oxygen is going to have a -2 oxidation number. So for hydrogen, it's going from 0 to +1, which means it's being oxidized, because remember, oxidation is loss of electrons. And oxidation is going to happen at the anode. And then for our oxygen, it's going to go from 0 to -2, which means it's being reduced. And remember, reduction is going to happen at the cathode. So now that we have that information, let's go ahead and start labeling this fuel cell. The first thing is we know it's going to be an alkaline medium. Since the most common basic medium for fuel cells is potassium hydroxide, I'm just going to write that in this specific fuel cell example. So now we have this fuel cell with a basic medium, and we have our positive cathode and our negative anode. Now, this fuel cell has a very specific membrane that is only going to allow negative ions to pass through it because of the basic medium that has hydroxide ions. So when the fuel or the hydrogen gas is pumped into this fuel cell, the hydrogen gas is going to latch on to this catalyst, which is normally platinum, and that's going to split the molecules into protons or H plus ions and electrons. Now those released electrons cannot travel directly through that electrolyte because it's only going to allow negative ion movement. Ions, not electrons. Instead, those electrons are going to travel through the external circuit from the anode to the cathode, which is going to generate an electric current that can be used to power a device. So now we have these electrons at the cathode, and then when our oxygen gas is pumped into the fuel cell, those oxygen molecules are going to get onto the catalyst and combine with those electrons to become O2 minus ions. Now, because this is a negative ion, it can now travel through this membrane to the other side, and when it does that, it's going to react with those two positive hydrogen ions to form water. And then that water is going to output here in the fuel cell. Now this should make sense, right? Because in the balanced equation, in order to make 2 moles of water, we need 2 moles of hydrogen gas. And we only used 1 mole in this example, so we only got 1 mole of hydrogen gas. Since the balanced chemical equation uses 2 moles of hydrogen gas, let's go ahead and run through this one more time so that we do the full chemical equation. So again, our hydrogen gas is inputted into the fuel cell. It's going to attract to the anode where it's going to get onto a catalyst that's going to split the molecules into H plus ions and electrons. Again, those electrons cannot pass through the electrolyte because only ions can pass through the electrolyte. So the electrons are going to travel through the external circuit and to the cathode. Once at the cathode, those 2 electrons are going to combine with that single oxygen atom to form O2 minus. The O2 minus will then travel through the medium and get to the anode. And once at the anode, it will then combine with those 2 hydrogen ions to form 1 mole of water. So that was a complete cycle of 2 moles of hydrogen gas combining with 1 mole of oxygen gas to form 2 moles of water that exited the fuel cell. All right, so let's deduce our half equations. So we're going to start at our anode, which is where hydrogen gas is being oxidized. Remember, oxidation is a loss of electrons, so our electrons are going to be on the right side of the equation. So from our balanced chemical equation above, we know we're going to have 2 moles of H2, and we know we're going to have 2 moles of water. So we're going to start there. And as you can see on the left-hand side, we have an oxidation state for hydrogen of 0. And on the right-hand side, each hydrogen is worth positive 1 oxidation number. So we have 4 of them. So that's positive 4, which means it gave away 4 electrons. So we have 4 electrons on the right side of the equation. Now at this point, we need to balance our charge. And since this is a basic medium, we're going to be balancing our charge with hydroxide ions. So since we have a negative charge of 4 on the right, we need a negative charge of 4 on the left, which means we're going to add 4 hydroxides on the reactant side. Now, before we finish, we need to make sure we have the correct number of oxygens and hydrogens on either side. On the left, we have a total of 8 hydrogens and 4 oxygens. On the right, we have half that. So we're going to go ahead and change that 2 coefficient to a 4. And that would be our half equation occurring at the anode. Now we can go ahead and deduce the half equation that occurs at the cathode, which is where oxygen is being reduced. So let's start with our reactant and product. So we have oxygen gas and we have forming 2 moles of water. Now looking at oxygen's oxidation numbers, on the left it is 0, on the right is a total of -4, which means it absorbed or gained 4 electrons. So now that we have that 4 negative on the left side of the equation, we need to add the 4 hydroxides to get the same charge on both sides. Now looking at this equation, you can see that there are hydrogens on the product side, but no hydrogens on the reactant side. So we need to add water to balance that out. So on the right side, we can see we have 4 hydrogens from water and 4 hydrogens from hydroxide. So it's a total of 8 hydrogens. So if we are using water as our source to add hydrogens, we need 4 of those waters to balance out hydrogens. And now we need to look at our oxygens to make sure those are balanced. And we do have 6 oxygens on both sides. So before we finish this, we just need to make sure that nothing cancels out. And we do have water on both sides. So this 4 would change to a 2. So our final half reaction at the cathode would be 2 waters combining with oxygen gas and 4 electrons to form 4 hydroxide ions. This would be your final answer for number 7, but just for fun, let's make sure we get our final balanced equation from these 2 half reactions to check our work. So we see that our electrons are going to cancel out. We also see that our hydroxides are going to cancel out. And then we can see that these 2 waters are gone and we are left with 2 waters here. So our final net equation would be 2 hydrogen gas molecules, 1 oxygen gas molecule, and 2 waters, which is the same as our original equation. So we know we're correct. All right, 8 says, one method of comparing fuels is by considering their specific energies. Calculate the specific energy of octane using section 7 and 14 of the data booklet. Now, in the past questions going over in this video, we answered our specific energy in kilojoules per gram. This is specifically asking for kilojoules per kilogram, so you do have to make that conversion before your final answer. So from the data booklet, our enthalpy for octane is going to be 5,470 kilojoules per mole. And our molar mass is 114.26 grams per mole, which is going to be 0.11426 kilograms per mole. So when we solve for that, we're going to get 4.79 times 10 to the 4th kilojoules per kilogram. And then part B says a typical wood has a specific energy of 17 times 10 to the 3rd kilojoules per kilogram. Comment on the usefulness of octane in wood for powering a moving vehicle using your answer to part A. Now it gave us the specific energy of typical wood in a slightly different format. So I'm going to change our answer for part B to 47.9 times 10 to the third, just so that we can accurately visualize the difference between the two. Now, as you can see, octane has a significantly higher specific energy than wood, meaning it provides more energy per kilogram. That's going to make octane a far more efficient fuel for transportation, as vehicles require a high energy to weight ratio for their performance. So since this specific question said comment on the usefulness, I would write that wood is less useful because it requires about 3 times more mass for the same energy. Or you could flip that in reverse and say that octane is more useful because it has a higher specific energy. Number 9, part A says determine the specific energy and energy density of petrol using data from sections 7 and 14 of the data booklet. Assume petrol is pure octane, C8H18, and it gives you the molar mass and density of octane. So we know to calculate specific energy, that's going to be the energy released or the enthalpy of combustion. That's from the data booklet. So for octane, that's going to be 5,470 kilojoules per mole. And our molar mass of octane, which we already got in the last question, was 114.26 grams per mole. So that's going to give us a specific energy of 47.9 kilojoules per gram. And then from there, we can go ahead and solve for the energy density. So to solve for that, we're going to multiply our specific energy by the density given to us. So that would be 47.9 multiplied by our density, which is 0.703. And that is going to give us 33.7 kilojoules per centimeters cubed. So that specific question gave you 1 mark for calculating the specific energy and 1 point for calculating the energy density. Then part B says outline why the energy available from an engine will be less than these theoretical values. So there are 2 different things you could have outlined in this question. One was incomplete combustion and the other one was heat loss to the environment. So in reality, an engine does not convert all of the input energy into useful work due to many inefficiencies through the process. So the 2 are incomplete combustion and heat loss to the environment. So the first one, a significant amount of energy is going to be lost as heat to the engine components and the surroundings. So internal combustion engines typically convert only 20 to 40% of the fuel energy into work, and the rest is going to be lost through exhaust gases and into the engine cooling systems. So with the IB mark schemes, one of the potential answers would be energy lost to the surroundings as heat. Another option for the answer choice for B would be to simply write incomplete combustion. Not all fuel is going to burn completely due to an insufficient amount of oxygen, so that's going to produce carbon monoxide and sometimes soot. All right, so our final question says identify the major constituent of natural gas and write a balanced chemical equation for its combustion. If you do not know this already, you do need to know that the major component of natural gas is methane. So you're going to write that methane, which is CH4, is the main constituent of natural gas. And then you're going to write the combustion equation for methane. So we know methane is a gas, We know in a combustion reaction, it's going to react with oxygen gas to produce water vapor and carbon dioxide. Then we're going to go ahead and balance that by putting a coefficient of 2 in front of oxygen gas and in front of water. And that is your answer for A, mark for the first part and a mark for the balanced chemical equation. Then part B is kind of lengthy with a total of 3 marks. It says compare natural gas with other fossil fuels as a source of air pollution for a given amount of energy and account for any differences. So IB was looking for 3 pretty specific things. The first is that natural gas is going to be the cleanest of the fossil fuels. That's because when it burns, it has a very high hydrogen to carbon ratio, which means it's going to produce more water than carbon dioxide. The next thing it was looking for is that the combustion of natural gas produces minimal amounts of carbon monoxide, hydrocarbons, and particulates compared to its counterparts of oil and coal. And then finally, they wanted you to mention that natural gas does contribute to global warming, but it does not contribute to acid rain. And the reason it does not contribute to acid rain is because it does not have the SO2 emissions, which would combine with the atmosphere to make sulfuric acid. Okay, so now we're going to go into part C. It says compare the relative supplies of natural gas and other fossil fuels. So I'm going to go ahead and erase this and make an easy to understand chart. So this one wanted you to compare natural gas to other fossil fuels, and normally when we're talking about other fossil fuels, we're talking about oil or petrol, and then we're talking about coal. So looking at the supplies, the first thing I want to look at is our abundance. So coal is going to have the highest known reserves, which means it could last over 100 years at our current consumption rate. Then next in line would be oil. We have about 50 years left of oil at our current consumption rate. But that does change a lot due to geopolitical and technological factors, but that's not really part of the mark scheme. And then natural gas does have slightly lower reserves than oil, but it is increasing due to new discoveries. Then moving on to our geographical distribution of these different fossil fuels. The first is natural gas. The natural gas reserves are super concentrated in Russia, Iran, Qatar, and the United States. So something that you could talk about in this question would be the uneven distribution around the world. Oil also has an uneven distribution. It's mainly going to be found in the Middle East, Venezuela, and Canada. And then coal is going to be the most distributed. It's not very distributed, but it is more distributed than natural gas and oil. And that's going to be abundant in China, the United States, Russia, and India. And so you didn't need to be this specific, but these are kind of the components of the mark for part C. But I will read you the actual mark scheme for part C, which is natural gas is the fossil fuel in shortest supply, and it is unevenly distributed around the world. Oil is expected to last a little longer, and coal, which is distributed more evenly around the world, is expected to last the longest. And that concludes our video for Reactivity 1.3 from the textbook. I hope this helped you. If you're still listening, great job. That was a really long video. I hope you have a great day.